All right. Welcome to the last 110L lecture. This is so sad. This is our last lecture together. We're so proud of everything that you learned this quarter. We've covered a lot of ground. We're going to just recap some of that today. Project 2 is due today. Let us know if we can help. We don't have quite as much flexibility for graduating students, but if you're not graduating, we have more leeway. And so let us know if we can either help you get through the project or if you need some flexibility on deadline. And then one more thing I forgot to put in here is same as last week. If you get a chance in the next a few days, please fill out the course survey and give us as meaningful feedback as you can. It's more important for this class than it is for other classes, just because this isn't like an official class. I mean, it's an official class, but it's, you know what I mean. It's not a long-term consistent thing with committed support. So if you feel that this material was important for you, please indicate that, and so that the department will hopefully either incorporate that into some other class or maybe continue this in some form. Yeah. So I was trying to think about what to talk about today and what to give as like a last lecture, try to come up with some unified themes. And I think I came up with 3 high-level lessons that you can hopefully take away in whatever context that you work in. They might be a little bit less actionable than some of the things that we talked about, like, I don't know, use a mutex of this form, or do this particular thing. But I think they're just things that are important to think about as you go on in your career and work in, whatever area of computer science you work in. These are still things that are important to think about. So the first broader lesson is make things hard or impossible to happen, which is kind of a given. So this isn't all that helpful because it's well, how are you supposed to do this? So 2 more slightly concrete suggestions are to use a strong type system to your advantage. Not all languages have strong type systems. If you're using just plain old JavaScript, then it's dynamically typed and there's not a whole lot of different types, and there's not a whole lot going on, but sometimes you can add things onto that. So with Python, you can add type annotations. With JavaScript, maybe you can use TypeScript. C also has it's a static type system, but it's not. We'll talk about C in a little bit, but maybe you can use C++, or maybe you can write portions of your code base in Rust or some other language. If you can, use a language with a strong type system, and then actually use that type system to your advantage. We'll talk about some more specifics. And the second kind of sub-lesson is design with a human user in mind. In systems, we're laying the groundwork for everyone else. We're kind of building the foundation. And because we're building things, it's very tempting to look at what the ground looks like and build our thing based on the ground. If we're designing computer systems, we look at how the hardware works, and we build something that kind of matches what the hardware is doing. But it's actually maybe more important to look up than it is to look down, to say, what is it that users of this foundation actually need, and to build things that fit that need well. I mean, you still have to figure out how to make that work with what's under you, but it's a very important consideration that is sometimes overlooked. And the third lesson is less about code and more about process. You need to look at your processes for how you're developing this software. And when mistakes come up, when bugs happen, you need to look at, how do I make sure that this doesn't happen again? What can I change about the way that I'm developing my code, the processes that I use to verify it and audit it and look for bugs and review it, and make sure that we don't keep making the same mistakes over and over and over again, so that you actually learn and progress in the quality of software, as opposed to just fixing one thing and then having the same mistake pop up again later. So I'll go through each of these 3. First, starting with use a strong type system. So let's actually look at a weak type system, which is C. And C is very, very frustrating to program in sometimes. It's a very simple language. There's actually not that much to it. You can learn most of C in 1/4 of 107, but it's hard to use correctly, and let's look at why. So let's imagine a hypothetical scenario that has nothing to do with code. Let's imagine you're a construction worker, and your boss tells you to connect the gas pipe in the basement to the street's gas main. Okay, sounds reasonable. You go downstairs and you find that this house doesn't actually have a basement. So maybe you decide to do nothing, or maybe you decide to attach the gas main to some other nearby fixture, or maybe the neighbor's air intake, or you do something and then you report back to your boss that you're done. When the dust settles from the explosion, you'd be guilty of criminal negligence. Yet this is pretty much exactly what happens in C. So in C++ or C, you can write an expression that is something like the string house of -1 times 37. And it's not clear what that is supposed to do. That makes absolutely no sense from a conceptual standpoint. Like, clearly something is wrong with that. And maybe it would be possible for the language to say that, hey, something has gone wrong here, but what does C and C++ do? They happily find some like non-intuitive interpretation of house of -1, one which might be different every time the program runs and can't be predicted by the programmer. And it grabs a series of bits from some place dictated by this wacky interpretation. It reliably assumes that those bits are meant to be a number, not even a character, right? This is a string, but it somehow treats that as a number, and then it multiplies that practically random number by 37, and then reports the result without any hint of a problem. And this is really frustrating, where you can write C programs that, you know, this clearly has some mistake going on here. You can write some code that may not be so obvious that something is wrong when you're writing it, but if you look back in retrospect, you're like, okay, yeah, something was definitely wrong here, and it would have been possible for a compiler to spot this bug, and yet the compiler says nothing, and it just happily compiles your code, and then some time down the road, you get a seg fault, and you have no idea what went wrong or why this happened. And also, when you're programming in C, sometimes you like encounter functions like this abomination. This is a process control system call. If you look at the man page for this thing, it's extremely long. I'd actually recommend like giving it a quick skim just to see how like hair pulling this frustratingly this can be. What's happening here is you specify a constant as the first argument here. That is specifying like what action do you want to do? And then the rest of these arguments are just like, they may or may not be provided based on which of these arguments you choose. It's kind of like a function with functions inside of it. And so you look at this and you're like, why are you the way that you are? This is like really frustrating. And so, well, why is this the way that it is, right? C was designed by some incredibly smart people. The reason that it is designed like this is C is very tightly coupled to the machine executing the code. Maybe not any particular specific architecture like x86 or ARM or something, but it's still very tightly coupled to some abstract model of a machine that executes code. Machines don't have notions of like vectors or generic types or polymorphism. And like process control is the way that it is because that's just how like system call and return works, like at an assembly level, not because it's convenient for anyone to think about it this way. That's just, you know, things are designed because that's how it works under the hood. And like taking a step back, let's talk about what a type system is. Types are the unit of dialogue in a language. Like when you talk in a language, what is it that you're talking about? And the compiler uses these types to figure out like, hey, what are you trying to say? Does what you're trying to say make sense? If you look at the type system of C, C's type system is oriented around like primitives, you know, like ints, bools, characters, structs, and pointers. I guess functions you throw in here too. Not a whole lot else. That's basically it. And when you write house of -1 times 37, the compiler tries to figure out if what you're saying makes sense in terms of pointers and like multiplication and numbers. And it verifies like, hey, yeah, that makes sense. This string house is just a pointer. You know, it's kind of an array in some sense. Arrays and pointers are somewhat interchangeable in C. You're taking the -1 index. That's fine. That's a reasonable thing to do in a context of an array. That is getting you out a number. You know, characters and integers, they're all just numbers from the standpoint of C. So we can multiply that by 37. That's a fair thing to do. And like this all checks out. Everything seems fine from that standpoint. And like C has a very small language surface, which is nice. You can learn like the whole thing in a short amount of time. But because you can't actually express that many ideas in this code, when you have ideas of like, I want to have a list of numbers and I'm going to put these things in and like, I want to iterate over this list, you actually have to do a lot of work to translate these ideas into C code. Like just passing a list to another function involves work. You need to pass a pointer to the list, and you have to pass the length of the list. And you have to make sure that you pass like the right length for that list, otherwise you're going to be in trouble. And maybe that's more work than we should be doing. Similarly, if you're reading C code, maybe you are trying to build on someone else's, or maybe you're trying to audit it and make sure that there are no errors that we should watch out for. If you're reading C code and you're just talking in these primitives, these like very basic constructs, it's very hard to build a mental model of what the authors were trying to do when writing the code, or what they were thinking when writing the code. If you were passed the pointer, were you passed the pointer because the author of that code didn't want to make a copy of whatever struct it's pointing to, and so you're just receiving a reference, but like you're not supposed to free this, you're not taking ownership of it, like whoever passed it to you, they just passed you a pointer so you can use it, but they're going to free the memory? Or were you passed the pointer because actually they're transferring you ownership of that buffer, and you are now responsible for freeing that memory in the future? How do you know? You can't really tell from the code. Sometimes you can tell from comments. Sometimes people will leave good comments, but from the code itself, you can't actually tell. When reading a code base, it may take a while to figure out what I was just saying, like, where is that memory supposed to be freed? What did the authors intend? And also, the compiler does not read comments, and so it has basically no understanding of like the intent of the programmer at a high level, at a like idea and concept level. So if you have access to a richer type system that allows you to express higher level ideas, then you should just say what you mean in the code at a high level, let the compiler compile that down to something that runs like at a machine level, but in the code, just say what you're talking about, and you can just like encode these ideas into the language. Right? Comments are great. So a lot of times you can say, okay, well, I'm passing a pointer to this thing. This thing happens to be, C has no generics. So if you want to store a pointer to something where that thing might be like different types, you have to store a void star. And then maybe in the comments you say, hey, this is a void star. It's actually pointing to this thing of like this particular type. The type is like maybe stored here. So on and so forth, and like, the size of an element is this, blah, blah, blah. But comments, and you can describe all this in comments, but comments can become stale, right? The code might change later on and somebody forgets to update the comment. This is like extraordinarily confusing. I worked at a company once that had like an over commenting problem, where they had documented everything so thoroughly that you couldn't change anything because you'd have to update the documentation. And then the documentation actually became useless because a good portion of the documentation was out of date. And if you're reading a comment, you don't know whether the comment is accurate or not, because there's a good portion of comments that are not accurate. And so you have to read the code anyways and figure things out anyways. And so like there wasn't much point to having the comment if you like can't trust what it's saying. And also, comments don't exist everywhere, or I hope they don't, because otherwise you're going to have the stale comments problem. Like you might, let's say that you're documenting when you're supposed to hold a particular lock. You have to choose in the code base somewhere to say, you're supposed to acquire this lock when doing this. Maybe you put it where the lock is defined. I don't know. But that lock might be used several other places in the code base. And say somebody comes along and is like trying to touch some particular value. They see this lock is being acquired, and they might copy and paste without going to the place where you wrote the comment. They might not see original comment. They can see this lock being used, but they don't know how it's supposed to be used until they go and read your comment and find it. And I've worked in places where, I've worked on code bases. Actually, in the Linux code base, this happens a lot, where there's not always a really obvious place to put a comment. And so somebody did write a comment explaining something, but they only put it in one place. And unless you've like read a lot of Linux code, you will potentially miss that comment and not know how you're supposed to use things. So if possible, you want to express what you're saying directly in the code. And if you express this in the language, the compiler can understand what you're trying to do, and it'll warn you if you do something dumb. And other programmers can better understand what you're doing just from reading the code, as opposed to having to go and read all your comments and find everything. So some quick examples that you've seen throughout the quarter: memory, like ownership. You'll read a lot of C and C++ code bases that write comments that explain, like what is happening with these pointers. This comment is actually a little bit complicated. what happens to this pointer depends on whether some other conditions hold or not. The caller is responsible for freeing star error P. So here, this is documenting ownership. It's buried in the middle of a 3-paragraph comment. You need to read this to figure out like what is supposed to happen here. Instead, it's better if you can make this explicit. Like in Rust, you can write a function that will take ownership and free the memory. If you write a function like this is saying that, you know, whatever parameter you pass here, this function is going to take ownership because this is an owned type. The ownership is part of the type system. Or if you want the function to just borrow a reference, like basically take a pointer to it, but the caller still needs to free, then you can pass it like this. And it's very clear, like without any comments, what is going to happen here in terms of like who's going to free this memory and who's responsible for it. And the compiler can sanity check what you're doing, and programmers don't have to read a lot of comments. They can tell what's happening just from the function signature. Another example that we saw is error handling. Like in what ways can a function fail? Sometimes people will write this in a comment or a man page. I have actually encountered man pages that like list, you know, they list the different errors that can happen, and they're not complete. There are actually other errors that can happen that were not documented in the man page because of like, you know, stale documentation. As the code evolves, sometimes people forget to update the documentation. And it's better if you can make this part of the code itself by putting this like in the function signature or somewhere else where the compiler can sanity check that, yes, this is actually accurate and true and up to date. And then anyone else using this, so, you know, this just is part of the code. Kind of a related thing. Yeah, so some languages use exceptions for error handling, and they will put in the function signature what exceptions that function can throw. And like that's a reasonable thing to do. In Rust, we opted for something different just because we didn't want to use exceptions. Exceptions have their own suite of problems. And Rust uses like enums to represent a range of possibilities. I think enums are a really, really good idea, not just in error handling. Like anytime that you need to represent a range of possibilities, you should be using an enum. There are so many places where people will just like pound define some arbitrary numbers or like just choose some arbitrary strings. And that is almost always a bad idea. For example, there was this like Linux kernel remote code execution vulnerability from lecture 5. If you want to go back and check this out, it's lecture 5, slide 16, where there was this function inside of the network stack that returns an int. So this is very common in C, right? You return an int. It's either 0 if success or -1 if error. And that's like a range of possibilities, except in this particular case, in this network stack, there were more possibilities. It returned 0 if success, -1 if error, and then maybe like 1 or 2 or some positive numbers for like success with some extra warnings involved. For example, if you're trying to send stuff over the network and it did succeed, but the network is congested and you want to say, hey, slow down, like don't send that fast. Then this would return this constant. I forget what the constant was called, but it was just like pound defined to some number that says like, hey, it did succeed. This was not an error. Like things are still going. You can still send, but you should probably slow down your sending because there's some congestion. And I actually like went through this code to try to find the comment that documented this, and I couldn't find it. I didn't look for that long, but it was like very much not obvious. Like this function here had no function comments. A bunch of the functions that it called have no function comments. I don't know where the comment is that says like, you know, it's going to return this constant for congestion, but like this is just an example of why it's not a good idea to just return an int to represent a range of possibilities. And then like try to rely on documentation. If you can make this part of the code itself, that's so much better. And again, I mentioned this like silly mistake ended up causing remote code execution within the kernel, which is about as bad as it gets. And it was like the fix was just a one-line fix. Such a silly, easily preventable mistake. And if you can use an enum instead and say like, hey, here's my possibilities. It's either okay or something has totally failed, or you know it's working, but you should be aware that like there's this other scenario happening. So another example is file descriptors. I'm just going to breeze through these. You've seen these throughout the class. Like this was some code that I saw a student write in CS 110. And they were like, why is my program not working? The compiler does not tell you that anything has gone wrong here. So again, the error is this closing parentheses is misplaced. It should be if close FDS of 1, close parentheses. FDS of 1 is what you're trying to pass to close. This is the file descriptor. If that equals -1, you're trying to do error checking on close, then say printf error closing. But that's not what's actually happening here. It's saying like compare FDS of 1 to -1. This is either going to output a 0 or a 1, depending on whether this is true or false. And then you're going to be closing 0 or 1, which is standard in or standard out, which is bad. And it compiles perfectly fine because close takes an integer. Booleans can be implicitly casted to integer. Life is good from a C standpoint. You know, there's not a whole lot to worry about here, not a whole lot of concepts that are actually in the language itself. We're just talking about numbers and function calls here. But if file descriptors were their own type, you know, if FDS of 1 was a file descriptor type and -1 was an integer and these can't be compared, then this couldn't have happened. You would have gotten a compiler error. And I would say you should get a compiler error here. This is clearly, obviously wrong if you look at this. Another example, which we didn't talk about so much, is authentication and authorization. So in the information security lecture, we talked about how, like, especially with copy and paste bugs, sometimes you can forget to check whether somebody is logged in, or you could forget to check whether they have the appropriate permissions to do the thing that they're looking for. And there were a couple examples we talked about. How do you prevent something like that? There are some pretty interesting solutions, particularly in Rust. So Rocket is a web server framework for Rust, and you can write code that looks like this. It's like really, really easy to get started with. It's really cool that this works. Basically, what this is doing is you define some functions that will be called. So for example, this is saying get slash. So when somebody sends you a get request for slash, basically like getting the home page, if you just go to the website slash, then Rocket will run this function, and whatever you return from this function, it will send back to the client. So if you return some string, you know, if somebody goes to your website and they go to, you know, mywebsite.com slash, then the server will respond with hello world as text, and that will just show up for the user. Like, this is a really, really small, quick and easy way to get started with writing a web server. Okay, well, what if we want to do something a little more sophisticated? What if we want to like load some information about all of the users on our website? And we also want to make sure that like whoever is logged in is an admin of that website. You can only list all users' details if you're an admin. Well, if you want to do something like that, you can write a function like this. You can say function super secret endpoint. Like if you go to slash get all user data, then it returns all the user data. If and only if you're logged in as an admin. So what's going on with this parameter here? Like, okay, we have this admin parameter of type admin. What is this type? What's going on here? This admin type is what is called a request guard in Rocket terminology. So these are values that Rocket extracts from requests and passes to our handler functions. If it's not able to build this object from a request, then it will just return an error to the client saying like, hey, you didn't submit the necessary information with your request. So like say somebody tries to go to slash get all user data and they're not logged into this website at all, Rocket will say, hey, I don't know how to extract an admin from your request. Like you don't seem to be an admin. I'm gonna return you an error. So how do we implement this admin type? Any request guard type will implement a from request trait with a from request function. So this from request, it takes a like request object with all the information that the client sent to us, and it will return an object of this type. So this from request function might like look at the request, check what the client sent us, make sure that it sent us valid credentials for an administrator. And if all of that checks out, then it will return an admin object, and then Rocket will call our function passing it this admin object. And then furthermore, like you'll notice I passed this admin object to these other functions like database.log access, like load, maybe this should be database.load user data admin. But you can say like, hey, in order to actually load data from the database about all the users, you have to have an admin object. And this makes like authorization part of the code. Like it is not possible to load user data without having a logged in admin. Because the only way to get an admin object is from this like request guard, which means it would have had to come from a request with like an admin that is actually logged in. And this makes it like, first of all, it's very clear from this code what is supposed to happen. Like you're supposed to have a logged in admin. And then also it makes it so that when you compile this down, like you can't fail here because there's no way to call this function without having an admin that's logged in. Any questions about this? I mentioned this briefly in one of the previous lectures, but we didn't really talk about it very much. All right. So yeah, that's like expressing what you mean in the code itself, as opposed to trying to like translate in your head down to these like primitive types and then trying to like comment, here's how you're supposed to use all these things. Kind of related is the second thing that I wanted to talk about, which is design with a human user in mind. UI UX spend a lot of time thinking about how to design things that are easy to use and hard to misuse. And I think this is a really important lesson for systems people as well. I think that we kind of suffer from what I'll call like macho gatekeeping systems culture, which is that like, hey, systems programming is hard, so you better be top notch and super smart. And if you mess up, that's your fault. Like you weren't smart enough, you weren't careful enough, and you should have done better. And like, yes, systems programming is hard. Okay, there's a lot of complexity involved, and you have to be very detail oriented and get the details right. Sometimes we do need to do things in complex ways to match what the underlying hardware and systems are doing, right? Systems programming is not hard because somebody just decided to make it hard. It's hard because there's a lot of moving parts involved and the underlying hardware is complicated. I don't know if any of you have taken like the EE classes with the like chip design. I have not, but I know a few people who have, and it's like, it just blows my mind. It's really complicated. But that's not an excuse to not try to find ways to design things that are safe and easy to use as much as possible, right? If you look hard enough, if you're just looking at the implementation, you say, hey, the implementation is hard, so my interface needs to be hard. That's a cop-out. You need to look at the implementation and say, okay, the implementation is hard. Is there a way that I can try to find some abstraction that creates an easy interface that I can somehow map to this very difficult implementation, right? You want to design with the client's perspective in mind. You want to design like for the client with the implementation in mind, not the other way around. You're not saying, hey, my implementation is hard, therefore I'm going to make your life hard too. If you expose a complex interface, every client has to deal with that complexity. Everyone who is building on top of your foundation has to deal with that complexity. Whereas if you expose a simple interface with a complex implementation, that might be hard for you to build, but you can do it once and you can move on. So when you are dealing with systems, right, you're not going to, nothing is magic. You can't take a very simple, you can't take a very complex foundation that you're building on and make like a super easy interface and like life is good. You're like, whoever's building on top of you doesn't need to think about anything. That's not what we're talking about here, right? That's magic. There's no magic solutions. We've seen this quarter. Like every great solution that we've talked about has some drawbacks that you need to be aware of. But I would say it's your job to take a complex foundation and build an interface on top of it that is like one level less complex than what you started with. Because that's really how we end up with simple code, is with layers of abstractions where each abstraction simplifies the ideas involved just a little bit. And it's your job to think about, okay, how do I make this easier? Not perfect, but how do I make it easier for the people who are building on top of me? So there are a bunch of examples, like all of Rust. Okay, many of the concepts in Rust are also present in C++. Like, this is not a Rust class. We've been presenting ideas that are present in Rust, but they're also present in C++. Like, for example, option is how you can return like a, either present or not without using nulls in Rust. C++ has a class called optional that does like the exact same thing. But in Rust, things tend to be safe by default, by design. Like somebody put a lot of effort, actually a lot of people argued a lot about how to make things as safe as possible, like with as few ways to cut yourself while still, having the same power and performance. And this is not really the case in C++. My personal opinion is that many people on the C++ like standards committee and the people involved in design take the attitude of, hey, like if you're going to be using this, you need to be top notch. And we're going to try to make things like as performant and as flexible as possible. Those are going to be our priorities. Safety is not the priority. And it shows. So optional is a thing that you can use in C++. There are 3 ways to get something out of the option, 2 of which are unsafe, like 2 of which can crash your program if you haven't done the appropriate checks to make sure that there's actually something inside of it. And actually the easiest way to do it, like the one with the shortest syntax, is one of the unsafe ways. So it's like really, really frustrating that it's designed this way. And it's an example of like an attitude thing. Like you need to have an attitude of, okay, I'm still going to make things fast, but I'm also going to make it a priority to make life better for the people building on top. For example, mutexes, like it's impossible to have data races with like if you put the data inside of the lock. Channels, like concurrency with shared memory is really hard. And as programmers, it's easier to think of like separate people passing messages to each other, right? This kind of maps more to reality where, I'm a thread, you're a thread, I'm going to send you a message, you're going to send me a message. And you don't have data races if you don't have shared memory. And like, that seems great from a high level standpoint, from like the standpoint of somebody, building on top. And if you're a systems programmer, you might discard this idea and say like, that seems great. I'm not going to do that because it seems like message passing is really expensive. If you have to copy all this data into these messages to send instead of sharing memory, well, that's too much work. I don't want to do that. But if you look at this from like a clever like problem solving perspective, there are ways that you can do this. And for example, in Rust, I think channels work extremely well. They can even be faster than shared memory with mutexes, where instead of copying all of the data, say you're trying to pass a vector, you don't pass the data buffer where all the vector data is stored. You just pass the teeny tiny like vector struct, which has like how many elements are this, what is the capacity, what is the pointer to the data buffer. You copy that, and then you transfer ownership such that like once you've passed that vector into the channel, you can't use it anymore. And this gives you the illusion of full perfect message passing with no shared memory, even though the implementation is sharing memory under the hood. And the implementation here for channels is actually very, very complicated, but the interface is so simple that once that implementation is there, it's very easy to use. Another example is like asynchronous programming. We just talked about this last week. Programming with like bare event-driven callback oriented, like non-blocking IO system calls. That's great from a machine perspective, but it's terrible for programmers. And here are some like example functions that David Mazieres wrote from his blog post, where he's basically like figuring out what is the state that is required at every stage, like what do I need to remember at every stage? And then he has like separate functions where you are passing that data like kind of from one stage to the next stage manually. And it's really, really messy, very hard to keep track of all of this and to do this correctly. But if you have the right abstractions and some ingenuity in the compiler, you can provide ways to write code that looks normal, but compiles down to all of this. Like, yes, it's messy under the hood. It has to be. This is how things work from a hardware standpoint. But let's try to simplify the lives for people using this. Again, this is not perfect, right? There are still rough edges. When I was explaining this to you, you still had to have some mental model of what is happening under the hood so that you could use these abstractions well, but you didn't have to be able to write all of this code. And I didn't write much code in those lectures either, because you just need to have a conceptual understanding. This is abstraction. You don't have to be able to do all of this yourself. I'll give you a non-example, which is database security. So in the information security lecture, we talked about how for a long time, like databases were actually insecure by default, which is clearly bad. Now they argue that they're secure by default, but I don't really buy it. So Elasticsearch claims to be secure by default because it doesn't accept remote connections when you install it. But is that actually really useful? Like, if you're going to have a separate database server and you want other parts of your application on other servers to talk to it, well, you have to have remote connections, right? This isn't very useful. So it's just inviting inexperienced sysadmins to open up the database to external connections without adding more security. And that's not great. Really, we need more innovative solutions to help not just secure by default, but where the secure solution is the path of least resistance in the way that clients actually use these things. So any questions about this, by the way? So the last lesson that I would kind of say is to make process improvements, not just to write better code, but to improve your processes so that when something bad happens, you don't keep making the same mistake over and over again. Not only that, but when other people make mistakes, you learn from the mistakes of others. All right, so writing good code is hard. You're always going to have bugs. It's an uphill battle. It's just reality. And like things are constantly changing. So I sort of think about like car design, like automobile cars. A long time ago, we used to think that building cars out of steel with very rigid frames was the safest way to build things. And intuitively, that makes sense, right? Like you want to be in a fortified vehicle so that if you crash, whatever you crash into isn't going to go through your car and hit you. It's like fortification seems like a good idea. Turns out that's a terrible, terrible way to build cars. You really want cars to, the problem with building a rigid car is that if you hit something, you stop like immediately. And that acceleration causes internal organ failure. And so it's actually better to build a car with designated crumple zones, parts of the car that are designed to collapse so that it absorbs some of that impact, some of that shock, and slows you down over a greater period of time. And we see this in programming too. Sometimes we develop something that seems like a good idea, and then through practice we realize, actually that's not such a great idea. Stir copy is a very simple function. It just copies a string. Seems fine. What could possibly go wrong? I'm sure that when people first designed stir copy, it was a totally fine idea. It's not until later that we have seen all of the numerous ways that you can get buffer overflows and other memory issues from stir copy. So you really need to institute processes that will catch problems early, prevent regressions, and help you grow based on emerging best practices, so that when things change, you can go back and identify old patterns in your code that are probably not so hot anymore. So what does the development process actually look like? I'll give you an overview of what it looks like at many companies. You implement whatever you're working on. You just do the thing. You submit it for review, maybe go through several rounds of fixes and improvements. And then once somebody else has actually read your code, a human has read your code and signed off on it, then you merge that into the code base. Eventually you release with a bunch of changes, and then you gather metrics, watch for signs that something has gone wrong. Maybe collect feedback from users. If you're working on a server, you'll have some logs, and you can say, okay, it's are errors getting logged that were not being logged before? That's probably not good. And this is how the process works. There's this thing called continuous integration, which is a technique, I guess, and also a server. So every time you push, you have a CI server that will take your code, compile it, make sure it compiles, and then do some basic checks to make sure that it meets basic standards. And this can happen every time you commit and push your code, a CI server can do this. It's a really good way to catch issues earlier in this process rather than later. You can imagine that if you go through this entire process without doing regular checks, then a human reviewer might not catch everything. Some bugs are pretty subtle. And if you release and you wait to gather metrics, well, if you have an error at this stage, that's kind of bad. You've already released it into the wild, things are already failing in production, and it'd be much better if you could catch it here at this very first bullet point before you even submit it for review. That way you don't waste the reviewer's time catching something that a machine could have caught. CI servers are becoming much more popular. They're very popular in like web application development, a little bit less popular in I don't know, command line tools and some stuff that C and C++ is often used for, but it's becoming more and more popular. And if you work somewhere or on something, like you should definitely be using CI to run automated checks all the time so that you have these processes in place. The processes are automated. You can't forget to run these tools because they're just part of your workflow. What do you want to do? Like, what should CI be looking for? What are these checks that I'm saying that you should run? Well, there's a lot of things. And this is kind of going back to the first week of this class. You should be running static analysis tools, right? You should be running linters. There are also more sophisticated static analyzers. We talked a lot about memory safety, but you can find any, like if you can frame the problem that you're looking for, if it's a specific code pattern that says you do this, and then you do this, and you pass this thing to this, and that's a problem. If you can frame that specifically, you can write a static analyzer to find this problem. There is a tool called CodeQL that was acquired by GitHub, is part of GitHub now. It's a really sophisticated general purpose static analyzer for many different languages. It catches all sorts of bugs in all sorts of applications, not just like systemd, C and C++ code, but in lots of other things. And like, yes, again, I mentioned at the very beginning, static analysis is not perfect, but it's a lot better than nothing. And it's definitely something that should be part of your workflow in a production environment. We also talked about dynamic analysis, right? Actually like run the program, watch what it does, and see if it does something bad. See if it like uses uninitialized memory or has a data race or something like that. This, again, is not limited to memory issues. If you can define the bad behavior you're looking for example, like with authentication and authorization, if somebody accesses sensitive information without having logged in, maybe that's something that we want to look for. You can build a dynamic analyzer that will like watch for that condition and raise an alarm when it happens. We also talked about fuzzing, which is like, you know, you generate semi-random inputs and you keep feeding them to a program, trying to make it do different things until it does something bad. And traditionally, fuzzing is used for memory errors, right? This is like these tools, many of these dynamic analyzer tools come from like a C and C++ memory kind of context. But this is such a simple technique and it could be used for anything. Like if you want to brainstorm after, I've done a little bit of work in the fuzzing space, and it's such a simple technique and such a powerful one where you're kind of just provoking a program to do new things and then just watching to see if it does something bad. In fact, you can even generalize this more and do more creative things. But many other there's a lot of room for creativity here. There's even other stuff. So I was just talking to somebody this week who was talking about a tool that he was using where they instituted this thing every time you change something in the front end code. So when you change like the HTML and JavaScript and CSS, it will take screenshots of like a bunch of different parts of the website in a lot of different browsers and compare them to the previous set of screenshots. And it will do like a visual diff, and it will say, like, as part of your pull request, as part of your review process, hey, you know, you made this change and here is the effect that it had on the website. Like, here is what actually changed if you load this in Edge or Chrome or Firefox or Safari. And, you know, most of the time, or hopefully, you see the changes that you intended to make, but occasionally you see like, oh, this button doesn't work anymore, or like, you know, this border radius, this button was supposed to be curved and it actually has boxy corners, and I broke something. And it's a really good way to find bugs in front end code. So there's so many different ways that you can apply these sort of techniques. Okay, Andrew says, we use that at Google and pretty much everyone ignores the screenshot diffs because it's extremely flaky and false positives happen all the time. Well, that's a bummer. I would love to talk about like ways that you can improve that. Because I think there are good ways to do this and bad ways to do this. And some ways are like more error prone and false positive than another. But that's a really good point that like if your tools have a lot of false positives, people will just stop using them because your results will not be meaningful enough. You really need to have tests, like automated tests that run your code check all the different parts. We kind of had a bunch of tests in this class, not a lot, but we had some. And you know how that works. You change the part of your code, you run the test to make sure you haven't broken anything. It might not seem very important when you're in the early stages of a code base, but it is so important as your code base grows. I've worked at places where like nobody wanted to change anything. They were too terrified of refactoring anything because they were worried that everything was going to stop working. Or maybe not everything would stop working, but like a tiny but very important feature would stop working that we forgot to test. And like manual testing is important, but it takes way too much time to do regularly on a sophisticated code base. Another important aspect to this is like, don't just write tests as you build features, write tests when things break. Okay, if you have a set of unit tests and you ship something and everything looks fine, and then you realize the thing that I just shipped, the thing that I released is actually broken, there are some bugs that slipped past the existing tests, go back and add a new test. Make sure that doesn't happen again. Because what will happen is in the future, somebody will refactor your code, they'll rewrite it. Like I mentioned at one point, I was talking about how Mozilla rewrote a component of Firefox in Rust, and they actually reintroduced some old bugs from the C++ code base. And that would have been caught a lot earlier had they had regression tests for that bug, some test case that said, you know, this was a tricky scenario, a tricky edge case. We need to make sure that we don't fail to handle this again. So just to recap, 3 lessons for you, or 2 or 4, depending on how you count. You know, use a strong type system to your advantage. Design for the human just as much as you're designing for the system underneath you, and make sure you look at process improvements, not just the code. So that's all I have for you, not for today, but for the class. Thank you so much for taking the class. I really enjoyed talking with all of you and working with all of you, and we really hope you had a fun time. This is supposed to be a fun class. This was like a word cloud from one of the surveys, like frustrating Rust assignment from one of the very first things. So hopefully this, hopefully you feel a little bit better, not just about Rust, but like applying these lessons to other languages, because there's a good chance that you won't, you're going to work on C and C++ in the future somewhere. So yeah, have a great summer, keep in touch, and we'd love to hear where you end up next. And what you do. There are, just a FYI, I'm going to post these slides. There are some extra slides here, like translating some Rust stuff to C++. I tried going through these last quarter and I felt like it just wasn't very helpful because you have to kind of practice this and write code using this. And if I just give you a whirlwind tour in like 20 minutes, you're not going to remember anything. So I will leave these slides if you ever want to reference them. But you know, you can look it up if you ever need this stuff, as opposed to just like trying to remember it because it's not great. Anyways, yeah, thanks so much for taking the class. Good luck with anything remaining that you have wrapping up, and feel free to stick around if you have any questions. Otherwise, yeah, have a good life. Keep in touch, and good luck with everything.